So for question 12, we have this full wave rectifier using a center tapped transformer. We know that we have on the primary 120 volts RMS with 60 hertz, it's a sinusoid, and the turn ratio is 96 to 12. So we need to sketch both the input and output waveforms on the same graph if the diode is ideal. What is the DC? So it's what's the average voltage at the output, and what be the peak inverse voltage rating for this case operate properly as a full wave rectifier. So if we look at the circuit here, first regarding the quantities here, so we have 120 RMS, so we have the ratios, so we know that the peak voltage, just change to black, so the peak voltage is going to be those 120 times square root of 2, and then Vs is going to be, so Vs is going to be half of that peak voltage, right, because we are like splitting the secondary into coils, so it's half of that times the ratio on the primary, the ratio on the secondary divided by the ratio on the primary, and this is going to give us ADS that it's 10.6 volts. Okay. Now, if we look at the circuit, on the positive cycle of the input, D1 is on, so we have current flowing. So let me just draw the two conditions. So we have two voltage sources here, right? And we have diode 2 here, we have diode 1 here, and then they both connect here, and that's the load. Okay, so in the positive half cycle of the input, right, because remember this one here it's grounded, so we have 0, right? So in the positive half cycle we have a positive value of Vs, so current will flow in this direction here all the way to the ground. Now it would be, if diode 2 was also conducting, we would have a current flowing in this direction to the ground, right? But because it blocks current flowing in that direction, that's not occurring. Okay, so this is the first half cycle. Now for the negative half cycle, we would have a current that's flowing in this direction here. Okay, and again, if diode 1 was then conducting, we would have a current flowing here, but it blocks that current, so that current doesn't flow. So during both conditions, when diode 1 is on or diode 2 is on, we have the current flowing in the same direction through the load, right? So because they are ideal, what we see here is that it basically fully converts the negative half cycle to a positive half cycle across the load. So if we would draw the input voltage versus the output voltage in the same graph, we have 10.6 here minus 10.6 here. This is voltage, this is time. Again, 1 over 60 for a full period, 1 over 120 for half of the period. We have the input here, right? Then the output would be, when diode 1 is on, we get this positive half cycle here. This should be superimposed. And then on the second half cycle, basically diode 2 conducts, but the current perceived by the load flows in the same direction. So the voltage at the output would be just the positive of that. Okay, so that's the overall V out and Vi that we have when they are superimposed. Okay, now if you look at the circuit here, let's say that let's say that we are in the first condition, in the first cycle, we only have current in blue here, and then we have already concluded that this diode, it's not conducting, right? But as you see, we still have 10.6 here and 10.6 here, right? So overall, if this is, suppose we have 0 here, right? And we are basically decreasing 10.6. At this node here, we have minus 10.6 volts. Now, because this is a short circuit, then exactly at this node, which is the same as this node here, we have 10.6. So the overall voltage, peak inverse voltage that this diode 2 needs to hold during this positive half cycle, it's 10.6 minus 10.6. And this is the peak inverse voltage for this case. So it's just 2 times Vs, which is 21.2 volts. Okay? We could do the same analysis for diode 1, but you just figure out that it's just the same thing. So in that particular case, then we would have minus here, right? So we would be just like the opposite, but the current, like the voltage, would be the same, 21.2 volts, but then during the negative half cycle. Okay. And for the average voltage of this question, we just have to analyze the waveform that we have here. So remember that the average voltage is equals to 1 over the period. So let's replace that by 1 over 60 is just like 60. Okay. Times. Now if you look, both half cycles, they have like the same shape, right? So it's just going to be 2 times the integral from 0 up to 120 of the peak voltage, 10.6 sine of 2 pi 60t dt, right? So this gives us an average voltage of 60 times 2 times 10.6 divided by 2 pi 60 times, so it's negative cosine of 2 pi 60t from 0 up to 1 over 120. Okay, so the average voltage is then 6.75 volts.